All right. So this was the autoencoder. And next, I want to describe a class of methods that make the dissimilarity matrices in the high and in the low dimensional space match. And I will try and create a huge table for this class of methods. So I cannot think of a short title. Methods that make high and low dimensional dissimilarities match. All right, and what we will have in this table are a name, then a dissimilarity measure in the high dimensional space, and the same in the low dimensional space. And then we'll have the objective of the optimization problem. And I might also have comments for these. All right, the first class of methods are called metric multidimensional scaling. And they proceed as follows. So in the high dimensional space, we can define a distance between points I and j, which I'm calling dij star. And that's simply the Euclidean distance. Then similarly, we have a dissimilarity in low dimensional space. So dij, oops, that would be not x, but zi minus cj. And a meaningful objective that I think everyone could come up with is as follows. We try and make these dissimilarities match as well as possible. So we look at dij star minus dij, and we square this deviation and we sum over them. This is an objective which is also called sometimes the raw stress. Okay. Unfortunately, this objective, it looks pretty innocent. Yeah? So we have Euclidean distances. Usually when we minimize squared deviations, these things turn out to be tractable. Unfortunately, not in this case. Yeah? So the minimization here would be argmin over the z's over the low dimensional coordinates. And you remember we had this qualitative discussion of when is optimization easy and when it is hard. And unfortunately, the set that we are optimizing over here is not convex. I'm very sad about this. Because, well, in principle, it's a pretty objective, but turns out to be hard to optimize. Why is that so? Consider 2 points. Let's say this is point here, x1, or we're talking low dimensions. So let's say this is point z1 and z2. And they have a distance, let's say a distance of 1. So I get a distance matrix out. My distance matrix would be 0, 0, 1, 1. But now I could exchange my points. I could have z2 and z1. They're still at a distance of 1. The distance matrix is the same, 0, 1, 1, 0. And now a set, and these are 2 legal low-dimensional coordinates, right? This is a legal low-dimensional embedding. Now, what if we try and meet halfway between these 2? Yeah? So if we try and interpolate them, well, then z1 and z2 will be at the same location. So z1 equals z2, and the distance matrix here will be 0, 0, 0, 0. So in other words, if I'm looking at the set of coordinates z that correspond to, so the set of coordinates z that yield a particular distance matrix, this set is not convex. And so why did I make this argument here? Because a set is convex if we can take 2 members of that set and then interpolate between them, and then at all intermediate positions we still want to be within that set. But here you see, as we interpolate the coordinates from the top and from the bottom, in between we get out a distance matrix that is different from its limiting cases. It's not convex. It is the boundary of a cone. And then you can find pretty mathematical treatments of, what is this space of distance matrices. So, for example, there's a nice book by Deza, if anyone is interested. Good. So, innocent looking, meaningful objective, unfortunately, a hard optimization problem. And then, of course, you can invent heuristics, and they will do quite okay, and so on. But we're not going to be able to find the global optimum in general. All right. Now, there's a variation on this theme, namely to consider not the distance matrix, but to take the squares of these distances. So sum over I, sum over j, and usually that is a bit easier. So if we take dij star squared minus dij squared, and again we minimize over z. this problem is easier, but still non-convex. Moving this down a little. Friendlier, but still non-convex. What do I mean by friendlier? Actually, you can find a globally optimal solution to this if you reduce the dimensionality by just one dimension. So Loiv found that out, but that doesn't, carry us very far. So to go from 10,000 dimensions to 9,999 is usually not what we want. And well, why is it friendlier? Because here, when we compute this, we have this square root involved that usually makes things extra hard. All right, and this objective here is sometimes called the S stress. Good, so that's metric multidimensional scaling. I've given comments on how they behave in the optimization. I can also comment on what do the resulting embeddings look like, and both of these so both these methods here, they emphasize the long distances too much. So, if we look at this square of deviations, it tries to get the long distances right more than it tries to get the tiny distances right. And when we want to unfold, that is not good. And this has prompted people to introduce weight functions. So, for example, there is salmon, who in 1969 came up with the following. So do you see where we are on the table? There, okay? I'm just zooming in so I can write. So in the salmon line, we are going to use pretty much the same thing. But now weighting by the distances. And salmon used the distances in the original, in the high dimensional space. By the way, when you read this literature, you need to be a little bit careful. When the authors talk about Euclidean distance matrices, you would think that this is the matrix of the D stars. But in fact, when somebody writes Euclidean distance matrix, they talk about the matrix which contains Dij star squared. It doesn't make sense. It doesn't make sense semantically, but that's the power of tradition. And accordingly, I'm also not totally sure, honestly, if salmon uses now the D or the D squared here. I don't remember. But the important thing is that okay, can somebody look that up and inform me? Manuel, maybe. Thank you. But the important thing is that these contributions are now weighted by the distance in the high-dimensional space to reduce the impact of that. Then, by the way, there is Kruskal, who a little bit earlier did something a little bit more complicated. Namely, he used not the distances themselves, but he tried to preserve the rank order of these distances. I'm only going to put it in words here. Because the procedure is pretty complicated, and well, anyway, you know, in our cases, where we're given points in high-dimensional space, we can compute all distances, so we don't really need to do this more complicated thing here.
So that formula is correct.
That formula, okay. According to Wiki, this formula is correct. Thanks, Manuel. All right. So preserve the rank order of distances, and this is then also sometimes called non-metric multidimensional scaling. So multidimensional scaling is usually abbreviated MDS. All right, and then it was a bit quiet for 30 years, and then in the late 90s, Desmartins came up, you know, with a tiny tweak that had a huge impact. So there's Desmartins, 1996, and he published a method called Curvilinear component analysis. So not principal component, but curvilinear component analysis, or CCA. And he took Semmon's formula and omitted the star. Okay, so note there's nothing here. Okay. So in Semmon, here we had weighting by the high dimensional distances. And here we have weight by the low dimensional distances. So are we talking about the same thing? Yeah. We have our original observations. We measure their distances. That gives us the d stars. We create low dimensional observations. We measure their distances d. We try and make them as similar as possible. And we just want to downweight the biggest contributions. Now, this innocent change, would you expect it to have any major impact? I think I did not, honestly, before I read the paper. And saw this picture here. All right. So what do we see? We have here 3 toy data sets. They are all 3-dimensional. That's in the left column. And then in the middle column, we have the result as obtained by this curvilinear component analysis and by Semmon's nonlinear mapping. So in the middle column, we weighted the long distances by the low-dimensional embedding distances. In SEM, we weighted them by the high-dimensional distances. And the impact is quite dramatic, as you can see in the first and the third example. So here we go from a nice, carving up of planet Earth to, a X-ray planet Earth. And here with these rings, he breaks up the rings, but they are always nicely separated. Here the rings, in the salmon case, they stay intact, but they intersect where in reality they do not. I guess in the case of the rings, you could argue, which one do you prefer? But in the case of the planet Earth, I'm very much here in favor of curvilinear correspondence analysis. So this weighting by low-dimensional distances, that's what the whole paper goes on about, allows for stronger or more nonlinear unfolding of manifolds. And Desmartines also introduces these interesting plots here of the distances. So for each observation, you can plot what's the distance in the high-dimensional space and what's the distance in the low-dimensional space. So we have d star along the one axis and d along the other axis. And you also see this small box indicated. And that is the weight function that he uses. So he doesn't use the distance itself, but he uses some weight function, which depends on the distances. So you've seen in this formula I've added w. And the weight function that he uses is the one that you see here. The weight function is 1 for close distances, so the short distances you really try and preserve, and it's 0 for the bigger distances. Then we don't divide by it, but if I write it like that, we multiply it by it. So excuse me, I should probably write times, apologies everybody, I should write times w of dij. And this has been a feature ever since, that it's the low-dimensional distances that are used for weighting. Good, that was Desmartines. But science goes on. And so does our table. The next was a paper called Stochastic Neighbor Embedding. Or SNE. That it was published by Hinton, who's one of the most important researchers in machine learning. But he also publishes a lot, and so other than this being a paper from Hinton, nobody paid really attention to this because it didn't work great. Now, what Hinton here did was to compare not dissimilarities, but compare similarities. So I should put a horizontal line here, because from now on we compare similarities. And the similarity that he used in the high-dimensional space was simply a radial basis function. So he used a kernel between xi and xj, where the kernel has been a radial basis function, or RBF for short. Now, a radial basis function looks like a Gaussian, but it's not normalized, and it usually does not have a probabilistic connotation. So let's say we have e to the minus and then some parameter times xi minus xj squared. And importantly, he made this parameter depend on the observation. So this is it's a radial basis function, but it has been scaled for each observation. And it was scaled by such that points which are in low density regions, they get a bigger kernel, and points that are in high density regions get a smaller kernel. And well, to find out what is low density or high density, usually you would need a kernel density estimate. And just like we discussed on Monday, instead of doing a proper kernel density estimate, he has been looking at the distance of the so manyth nearest neighbor, and then used a heuristic formula involving something called perplexity. But the bottom line is that we get a scaled kernel for each observation. And this was in the high dimensional space. And then in the low dimensional space, he used a kernel between Zi and Cj, also a radial basis function. And to now make them, to find a good low dimensional representation, he was minimizing the Kullback library divergence between, let me call the first k star and the second one k. And this is again over all pairs I and j. And this thing was again minimized over all z's. Okay, so he tried to make the high and low dimensional similarities match. That's all very reasonable and did not work great at all. Now, I've been mentioning this because the successor, the next paper, has been the state of the art for a decade. The successor, that's the famous t-SNE. t-SNE, pronounced t-SNE, by van der Marten and Hinton. In 2008. They used the same kernel in the high dimensional space, but in the low dimensional space, they did not use an RBF kernel, but a student T kernel. So 1 over 1 plus some parameter times Zi minus Cj squared. So as you know, the student t distribution has a much, yeah, go ahead.
Sorry, in the SNE case, what does the KL stand for?
Oh, excuse me, this is the Kullback-Leibler divergence. So Hinton made a big probabilistic argument, but I don't really buy it, which is why I give this very boiled down summary of it, of selling this to you as just similarity measure. And now in t-SNE, this student t kernel has much heavier tails than the RBF kernel, and this turned out to have a huge impact. So the objective was still the same. It was Kullback-Leibler divergence, but let's look at some. Okay, I don't have a comparison plot, but this small change of how do we measure the dissimilarities in the low-dimensional space, again, made a huge change to the quality of the embeddings that could be obtained. So I'm scrolling back up to the beginning of today to show that here t-SNE in this column, it's pretty spectacularly good. When it came out, nobody could believe that it managed to MNIST as well. And even with fashion MNIST, it's very respectable what comes out. Okay, so that's on the good side. On the bad side, it is, of course, again, a non-convex optimization problem. And so a few tricks are needed to bring it to convergence in a reasonable amount of time. For example, the authors use a scheme which is called early exaggeration, which can be thought of as a step size schedule, and that is really important to make it run well. And in t-SNE, points are initialized randomly, and this can lead to some strange results. I'm looking for a picture. This one here. Now these pictures are not from a t-SNE paper. It's a paper from Linderman, Steinberger, and they give these somewhat mean examples. Yeah? So here on the left is the input, a straight line in a three-dimensional space, and the task is to give a dimension reduction of this straight line to 2 dimensions. And of course, the optimum answer, is a straight line in 2 dimensions. But you see on the right-hand side, the pretty creative embedding that t-SNE finds. And well, this is a testimony to the hardness of this optimization problem. Yeah, so t-SNE works by initializing points randomly, and then it has a hard time. Well, it finds a pretty good local minimum, but not a perfect one, as you can see here. And on the bottom, well, the Swiss roll, it's been rolled many times, but the perfect unrolling would just be a rectangle. And again, you get something distorted. But I think the first example is still, it's more impressive still. All right. Now, probably, at least the first problem could be fixed by initializing with a deterministic procedure. If you had initialized t-SNE here with PCA, you would have been just fine. Good. Then, by the way, in these optimization problems here, the way I've written it, we've always been minimizing over all coordinates in this low dimensional space. So if we want to embed 1,000,000 points, then we have 2,000,000 coordinates to optimize over, because each point has 2 coordinates. That is a lot. So instead, you can also use a neural network to embed your points and then still evaluate the same objective. That would be called something that could be called parametric t-SNE, or there's a paper called like this. And this same trick can be used for all of the methods in this table here. All right, and now the final one, the final entry in the table is a method called UMAP. This is an abbreviation for Uniform Manifold Approximation. This is by McInnes. And is not so well known yet. And this is better still than t-SNE. Yeah? So t-SNE ruled for 10 years, and I think we now have something that works a little bit better still. Now, if the paper has beautiful 20 pages of pure math, and a lot of topological arguments are being made, and what they lead up to in the end is a different similarity kernel in the high dimensional space. So what these authors find useful is the following. So the similarity kernel that they use is constant up to the distance of the nearest neighbor. And of course, how far that nearest neighbor is away, that's different for each point. And it then starts decaying exponentially with some parameter kappa I that, again, just like in stochastic neighbor embedding, is found separately for each observation. So again, in low dimensional spaces, this falls off more slowly. In high density regions, this falls off faster than in low density regions. And the density, again, is estimated in terms of the distance of the so-and-so manyth nearest neighbor. And in the low dimensional space, they use a single-sided exponential, also potentially with a small, I think, unimportant offset here. So this is here a single-sided exponential function. That's the kernel in the low dimensional space. Now, to optimize, they use not the Kullback-Leibler divergence, but the cross entropy. So they minimize over Z, sum over I, sum over J, the cross entropy between this kernel that they defined in the high dimensional space and the kernel that they defined in the low dimensional space. They don't initialize randomly, but they initialize using Laplacian eigenmaps. One of the methods that I won't have time to introduce today. And let's see if I have a pretty picture somewhere. Yeah, at the very beginning I had one, right? The plot I showed initially today showed you pretty spectacularly good embeddings. On the practical side, UMAP is also faster than t-SNE and is hence very interesting. Now, McInnes has a nice paper, but there is also, if you're interested in reading up on UMAP, there's also a great blog called How Exactly UMAP Works. By Oskolkov. And I'm mentioning it because it describes the same method, UMAP, but if you look at the paper, if you look at the blog, it's very different. It's the same method, but it's very different views on the same thing. And well, I think I would suggest you start with a blog, and you can then read the paper afterwards and look at their very pretty pictures of prime divisibility that they have at the very end of their paper. Good. So why this grand table? To show you there's a huge number of methods out there. The very underlying ideas are actually, few. In the top half of this table, we try and make dissimilarities match. In the bottom of the table, we try and make similarities match. I have many more famous methods that fit into this table, but no more time. But I hope that this will, give you the intuition behind these methods. If you really had to use one today, I would start by PCA and then do UMAP next. Thank you very much. See you Monday.